Hello everyone, welcome back to 3 Deviations. So in the last video we introduced the substitution rule, which basically was the reverse of the chain rule. So if I have the chain rule, which says if I want to take the derivative of f of g of x, well, that produces f prime of g of x times g prime of x. Now the substitution rule says, well, how do I do this in reverse? It says if I have the integral of a function f of g of x with the g of x derivative in there as well with respect to x, then I can make a substitution and write f in terms of u with respect to u, and then this should be an integral that I'm able to compute. That's how the substitution rule works. So we're going to do an example of the substitution rule today, and then we're going to follow that up with many more videos with these types of examples, just since they're very helpful, and this is something we want to understand really well before we get started. All right, so up here, I'm just going to restate the chain rule. So the chain rule says if I have the derivative of f of g of x, then that becomes f prime of g of x times g prime of x. And I'm going to keep that up there just so that we can remember what we're doing. Now, I urge you to pause the video and try to evaluate this integral using the substitution method. So you can pause it and see if you can evaluate it. Then I'll also put up the substitution rule here as well so that we can remember it. So we have integral of f of g of x, g prime of x dx equals integral f of u du. All right, so now let's tackle this guy. So as you might be able to tell, this is an integral that if we wanted to, we could evaluate it with the sum rule, but we just need to do a ton of algebra. We need to expand that binomial to the 9th power. That would be quite a lot of binomial theorem and Pascal's triangle that I don't think we want to deal with yet. And then we need to multiply it by that 2x plus 5. Again, not something I would think is very fun. So we can do the substitution instead. As we can see, this x squared plus 9, x squared plus 5x to the 9th is our main function. And of course, this x squared plus 5x is the inner function. And then we have that operator to the 9th power on the outside. So now what we can do is we can think about what our choice of change of variables is going to be. So what should we set u equal to? Well, as you remember from the last video, we were told that always setting u equal to the inner function is a good idea. And we should also see if we differentiate that inner function, if we see that anywhere else inside of the integrand. So if I set u equal to x squared plus 5x, let's try differentiating this. That goes to 2x plus 5. Well, we have 2x plus 5, and we don't even need to manipulate that at all, but we have that 2x plus 5 right there. So if I were to choose u equals x squared plus 5x, that would produce a very successful change of variables. So why don't we do that? So we're going to take u equals x squared plus 5x, and then when we differentiate that, we take du equals 2x plus 5 dx. All right. So this is really good. Now we can substitute everything back in. And as you can see, it just falls in really nicely, and we are left with an integral of just a power function. That's really easy. So we have the integral of u to the 9th with respect to u, and of course we just use that nifty reverse power rule, and that gives us 1/10 u to the 10th power. All right, so now that we have that, all that we need to do is we need to substitute x back in for u. So we already have up here that we already know what u is equal to, so we just need to plug in x squared plus 5x wherever we see a u. And that gives us 1/10 times x squared plus 5x to the 10th power. And of course, adding in that arbitrary constant of integration there. All right, so that is how we do another substitution there. In the next video, we're going to come back. We might talk about some more complicated substitution examples. And then after we do a couple of those and we feel good about that, then we're going to do some definite examples, because taking a definite integral with a substitution is a little bit harder than you might think. and there are many ways that we can do it. All right, so we'll see you guys for that video. Bye-bye.